movement disorders was just always something that I was very, very interested in. I really enjoyed actually this study from the point where I thought about something to translate it to a task. And I think a lot of times when people in academia start, they feel this pressure and they think about what should I do, how should I behave, and what are the questions that I should ask. And I think at the end, you're really responsible just to live the life that you want to live and work on the things you want to work on.
Welcome to Stimulating Brains.
Welcome to Stimulating Brains. In this episode, I'm joined by Dr. Roxanne Lofredi, a prominent researcher investigating movement disorders and deep brain stimulation. Dr. Lofredi is based at Charité, Universitätsmedizin Berlin, and is widely recognized for her groundbreaking contributions to understanding how basal ganglia networks drive motor symptoms in conditions such as dystonia and Parkinson's disease. Today, we'll explore two fascinating studies led by Dr. Lofredi. The first focuses on how subthalamic nucleus stimulation impairs stopping of ongoing movements in Parkinson's disease. This work, published in Brain, was inspired by foundational basic science study from Aron and Poldrack 2003, which first implicated the subthalamic nucleus as a critical node for motor inhibition within the hyperdirect pathway of the basal ganglia. We'll discuss how these findings translated to her DBS study and how they may impact DBS therapy. And then the second part of our conversation will cover her recent publication in Nature Communications, where Roxanne and her team demonstrate a clear link between striatopalliidal oscillatory connectivity and symptom severity in dystonia. This work highlights the pathophysiological role of the direct pathway within the basal ganglia and opens up new possibilities for targeted therapeutic approaches. Roxanne, welcome to the show. Thanks so much for joining us.
Thanks for inviting me, Andy.
So as you know, I typically start with an icebreaker question, which is what you enjoy doing in your free time. And you are in Portugal and you have a young kid, so I can imagine, but maybe there's something to tell here beyond that.
Yeah, I think I was, when I saw, I mean, I know you're a podcast writer, and I know that you're starting always with this question, and was thinking about that. And of course, having had my first child 8 months ago, my free time is basically covered by him. And then I also started full-time clinical work 2 months ago now, so even less free time for me. But I guess before that, and I think that hopefully at some point I will reach that again, I had never really had some big hobbies or so. I think I always had this kind of classical bourgeois bouquet of activities where you do your sports, which was swimming in my case, your music, playing the clarinet in my case, and reading a lot. So very typical, I guess, for our bubble.
Bourgeois bouquet, love it. And I think you also know the party scene in Berlin quite well, right? So there has been some experience there in the nightlife scene.
Yeah, and it's so you're saying already a lot of things about me, like being in Portugal, she's not working, she's just on vacation and then partying all the time.
Well, back in the days when you were young, of course, to clarify, yes.
Sorry, when I was young. This starts very well. No, yeah, of course, I think I like mainstream culture, but I also like subculture. So Berlin is a perfect spot for that.
And then Barbara Holunda asked the guest question that I didn't understand really about Zendaya. Who's Zendaya? What's that?
Referring to the mainstream Yeah, then who's Zendaya? You were
Yeah.
asking? Oh.
I mean, I Googled her and I, found
Yeah.
out something, but
I think that's just translating that I'm very fond of pop culture and pop stars, and I like fandom, and I have a lot of fandom for people like Zendaya or other just mainstream pop stars. I think Barbara was highlighting that because sometimes people are a bit surprised about the knowledge that I have.
so what's your favorite fun fact on her?
On Zendaya,
Yeah, that was Barbara's
um,
question.
I think I just felt very connected to Zendaya because Zendaya and we have the same fetish over Beyonce. So that's why I just feel close to her.
Love it. Okay, so moving on to more serious matter and your career and your work. Could you share with us some of your key mentors and turning points in your career that led to where you are now?
Turning point. So I think one very important moment in my life that introduced me to science or to neuroscience more specifically was when I started my thesis in Paris. So I did a very basic neuroscience thesis on patch clamp recordings in the parahippocampal area in Richard Miles and Desdemona Fricker's group at the Institut du Cerveau et de la Moelle Épinière, ICM, in Paris. And I really appreciated the environment there because it was a very new brain center somehow, and they wanted to start this new culture where a lot of different neuroscientific groups are working together. And I really enjoyed the environment there and learned a lot. And there were many people from different fields coming there giving talks, and I worked primarily with neuroscientists, not so much medical doctors.
Mm-hmm.
And it's a very different school of thought, I think, than coming from this clinical perspective. And I found this very enlightening somehow. Yeah, so I think this was definitely a turning point, also a point where I thought, yeah, I think I want to integrate this, not only being a clinical person or neurologist, but really aiming towards this goal of being a clinician scientist, which was very, very difficult, I think, and contradictory in many situations. But yeah, so this was a turning point for me. And then, of course, meeting you, Andy.
Just for the audience, this was a joke. Yeah.
No, it wasn't a joke. We met when I came to Berlin, actually, and we were in a very weird course, and I was just bored at that time, and we talked, and I think you told me about Andrea Kühn's group and what you're doing here in Berlin, and yeah, I really enjoyed meeting you, and I found very interesting what you told about the work of this group. So you were a turning point then for me.
Interesting.
Well.
I didn't even, I don't even, I remember it slightly differently. I think you even asked me about Andrea. So you already had, your eyes set on doing something invasive in humans and so on. So,
yes,
so
definitely.
yeah, I probably wasn't the matchmaker for bringing you into the field of DBS, but it's funny that I remember that course too. Yeah, great. And remind me, did you study in France, medicine, or in Germany?
I started studying medicine in Germany, in Heidelberg, and then I moved to Paris because in parallel to my medicine studies, I studied psychology as well in Paris.
Cool.
And so I did then like this year abroad, but continued there and started my thesis then there. So I lived for 5 years in Paris.
Oh, fantastic. Yeah, such a cool face. Didn't even remember that. Okay, and so okay, you met me, but I think more importantly, you also met the group of Andrea Kuhn, and what happened then?
Yeah, so I when I moved back from Paris, where I worked, as I said, in the rodent model, I really wanted to kind of shift back to the human, because after all, I started to study medicine and I wanted to work with humans and help humans and be directly in contact with them, not only in the clinical work, but also in my research work. So this is why I wanted to maintain kind of what I learned about electrophysiology and neurophysiology from the animal models, and explore how I can translate this to humans. And then there are two major fields, right, where you can do electrophysiology in humans, or at least direct intracranial recordings in humans, which would be epilepsy and movement disorders. And movement disorders was just always something that I was very, very interested in clinically, because it's, yeah, I think so various what you can see there, but also you always also have the possibility really to help people there, for example, with Parkinson's disease. And that's pretty rare in neurology. So
Sure.
enjoy this. And so that's why I was more drawn clinically to movement disorders. And then I learned about the work that Andrea is doing with, or did at that time already, with intracranial recordings in movement disorders. And that, of course, then merged two of my fields of interest.
Yeah, yeah.
So that's
How did you get interested in then, maybe the physiology of movement? Was that before that time, or was it really driven by the clinical interest?
yeah, so in movement per se, I mean, in movement disorders or in Parkinson's disease, I think I was more interested at that time, and I think that's also something that is often so in the cognitive part and limbic parts and the emotion and the thinking, and coming from psychology too, that was of course more, or not of course, but I think oftentimes that's something where students are easily drawn to,
Yeah,
not so much movement. And I think movement was something that I then got curious about in this context of having already had some experience with research work, because I just felt that movement is a safer readout parameter and less prone to confusion of concepts. And so I think this is something that I more enjoyed from a pragmatic point of view also, in when thinking about how my future in research could be and what could be the research questions that I want to address, and also knowing that I'm, of course, I mean, that's the case for a lot of scientifics. I think that they are questioning their results and not sure whether that's really true what you find. And I think with movement, that's just sometimes easier.
So if
Than
it's
with
so
those
easy, how's that going? Understanding it. No,
I mean, that's
I'm
yeah.
joking, but I have to add the anecdote. I interviewed Günther Deutschel on this podcast, and he told me that he chose tremor as a simple sign and
Yeah.
thought that's something he can clarify in his career, and then, he retired without having clarified it in a way. So
Anything.
yeah,
No. Yeah, no, of course. I mean, it remains challenging. It's not that
yeah,
it's easy. It's just
yeah.
easier, maybe, or not easier. It's just
You have better
it.
readouts, absolutely.
Yeah,
Yeah,
you have better readouts. You can feel more confident about what you're reporting. It's more graspable in some kind,
yeah.
but in some way. But of course, it remains very difficult. And Günther Deutschel didn't had so many decades and didn't find find the final solution on how and why and where trauma is generated and how we can stop that. So of course I didn't too for my very
Yeah, yeah, yeah.
short visit
Not
now.
yet. You have time.
Yeah.
So diving into that, you published many really fantastic papers already. I kind of picked two, which might be your highlights, but it could also be that you have other favorites. So we're more than happy to diverge off, of course, too. But the first one is you published that in 2020 in Brain, and it is a study where you tested the effects of DBS on versus off during a motor task, and that's a motor stopping task. And what I personally love about it is that it was really very hypothesis driven, right? Which is not always the case in these DBS group studies that also my lab does and others do. But you had a clear hypothesis, and that hypothesis was based on a very different field in a way, right? From the neuroimaging field, Russ Poldrack and Adam Aron. So I would love to maybe start with that basic science work, and you can talk a little bit about that, and then how you came to the idea of trying this in DBS.
So you mean what the concept is of?
Yeah, the Aron study, if you can maybe walk us through. I think it was even his thesis in 2003.
Yeah,
what did they find?
And then of course I think it's he just expanded it more and more over the years. So it's the idea that you have a network that can be associated at the end, or what his final conclusion was, then globally with inhibitory processes in your brain, pretty much independently of what the exact context of this inhibitory request would be.
So you're saying stopping a thought or stopping emotions would have the same general network than stopping movements. Okay.
Yeah. But he started, so he's also from coming from this more psychological side, and he started with this classical stop signal task. So it was pretty much in the cognitive domain. Everything was more related to this cognitive domain, and also to the inhibition needed in the presence of conflict. So you have a situation that is not clear from the start, and it becomes clear maybe over time, and you have to withhold something, and therefore act, or therefore inhibit some kind of activity. But it was really in this context of conflict. And I think for me, oftentimes when I'm reading papers, or no matter from which field they're coming, or what method they're using. So here in this situation, it's really the neuroimaging domain, but of course he expanded to electrophysiology, but still its first studies were neuroimaging based, is always to think about how this can translate to what I'm doing, or whether that's something that could be used or integrated somehow in what I'm doing. So I'm always trying to expand methods. I'm always trying to see whether concepts that arose somewhere else can be translated to the place where I'm at. And in this situation, I really read about this cognitive effects of deep brain stimulation, because he also looked at the effect of DBS on cognitive inhibition. And I think all of the people working with DBS know these effects of DBS on impulsivity and making patients more impulsive in some contexts, not always, but
this is mainly SDN, DBS, and Parkinson's, right? Yeah.
DBS and Parkinson's, where you can observe then that you can have side effects that you want to avoid in the clinics, of course, where people can even change their personalities. And this, of course, then being something that was very salient for me when I started with DBS, because that's something that touches the concept of the mind and the personality. So it's pretty salient, I think. And then me being more in this motor domain, I just thought of how with this concept something that is translatable, because I didn't ever buy so much into this division of the subthalamic nucleus, where you have this cognitive domain, the limbic domain, the motor domain, and something that be like little rooms apart and in one house, but separate rooms. This was conceptually pretty difficult for me to grasp that it would be like this. So I think that's why I thought of, could this be a phenomenon more globally speaking and not something restricted to the cognitive domain? And that's something that you see in Parkinson's disease, right? You can also see disinhibition in movements, which would be dyskinesia, these involuntary movements that you can have either with dopaminergic medication, but also with subthalamic DBS, and then of course also lesions, where you can observe those disinhibited movements.
Yeah.
So I was just wondering whether this could be a similar readout actually of this inhibitory network that was more related to the cognitive domain before that, but whether we could link movement disinhibition to this network as well.
Yeah, maybe to just before you go into details there, to briefly make 2 points. So first of all, remind me, I imagine from the original Poldrack and Aron stuff that you, in your talks, for example, there was sometimes just to draw an image, person driving a car, and then there's maybe something crossing the road, like an animal or so, and then they have to stop, right? And that conflict, is that a correct image just to draw from the original work? And then also, I think it's critical to mention that they found activity in the STN, right? So they found the stopping triangle, right, lateralized, and it had a peak in the STN. So then, the STN DBS, parallel makes a lot of sense. But are these two things correct? Maybe you can briefly clarify.
So the image of the driving car and stopping, I think originally it was more this idea of you have to choose between two things or withhold a decision.
Okay, so more cognitive conflict. Kind of. Okay.
Yeah. So this was the original context of it. Then what was the second? Sorry,
But it still involved the STN, right? Yeah.
Exactly, it's the right hemispheric inhibitory network between the pre-SMA, the right IFG, and the right STN. And that's always this very nice picture that you see between those three nodes. So the pre-SMA, IFG, and this little small STN.
So stopping triangle, because it's rare that fMRI studies like the ones involve something like the STN, right? These nodes of activity are often discarded, or I think, it's noise, it's too small, whatever. But okay.
That's maybe something that you know better then, because as I'm always focusing on the basal ganglia, my feeling is that there are a lot of fMRI studies involving the STN.
You're probably right. There certainly exist, but I think they often, for example, the cerebellum is another one. Oh, we have this big blob there. We don't know what it means. Let's just maybe not make a big deal out of it. I think at least back in the day, that was often the case, where people were just cortex-centric in their views.
Possibly. That's always then this kind of window that you're looking through, right? And for me, it's the basal ganglia. So I'm kind of filtering and don't see all this other stuff. But it's true that, for example, when I went the first time to Neurocontrol of Movement, this conference that I really enjoyed actually, in 2018, I was just also very surprised of how little the basal ganglia are represented there, because for me, I always thought of course, the basal ganglia are center of control of movement. But there are definitely other brain areas that are very important as well.
Yeah. So, but I interrupted you. So you saw that stopping triangle and you thought, can we bring this into the movement domain and analyze it with DBS?
Yeah, can it be something that that explains a clinical observation. I think that's always this situation that you find yourself in, right? If you're doing clinical work and scientific work, is that you have this ping pong of observation. So you read papers that may inspire your thinking in the clinical routine, but you also observe things in the clinic that back and forth and inspires research questions. And I think this was just this situation where I read this paper and saw this triangle and saw what it that it was associated with disinhibition, and observed this phenomenon in Parkinson's disease patients of this disinhibited movements. And I just wanted to know whether that's something that we can bring together. And then, of course, the brain stimulation is just a very, very powerful tool to probe circuits and effects on circuits. So, yeah, I think this was pretty much what I wanted to do. And then I had to think about a task, right? Because there wasn't really a task addressing this, because most tasks investigating inhibition, we're using the stop signal task. And if we're frank, in the stop signal task, there's just no movement, right? If the patient performs successfully, they just do nothing, which is good, but it's just not.
It's not an ongoing movement. Yeah.
It's not. Yeah. It doesn't allow you to investigate the precise effect on movement, because there's just an absence of movement.
Yeah.
And that's why I wanted to then design a task where we have movement and where we can say it's a continuous movement. It's not something where we have breaks in between movements, because often we have tappings or single button presses or something like this. It's difficult then to, because you have very separate sequencing within the movement that makes it then difficult to assess the effect on a continuous movement. And that's why I then thought of this circular, rotating, continuous movement, where we really have this stopping signal and see what does it on this.
Yeah, so for the listeners, we should clarify. So I think you came up with a graphical tablet, which I think is genius in itself for tasks, right? And then you said, okay, they have to draw circles, big circles. So I think they had to use proximal, like the whole arm essentially, to do this. And then, then at some point there's a red light and they have to stop, right? That was the core of the task. Yeah. Okay.
Yeah, exactly. Pretty simple. Not a very difficult task neither to design or to understand. I think it's just, as you said, the person just draws circles and then at some point has to stop following a visual cue. And this allows you then really to see the effect of this stopping signal on an ongoing movement, and without having to calculate some kind of reaction time delay due on a lack of movement. But yeah, it was, I really enjoyed actually this study from the point where I thought about something to translate it to a task. And then also just, it's such a good feeling when you have an idea and a hypothesis, and then you design a task, and then you test it, and then it works out. It's just cool.
Absolutely. I mean it's we haven't gotten to this part, but I was blown away that how beautifully you essentially replicated the stopping triangle with this. And so just to briefly add on to this, you of course did the task without DBS and then under DBS, right? So these were the two conditions. So essentially you introduced a causal circuit manipulation with DBS, and that was onto this exact circuit, because the SDN is one node of the three. And were you thinking of DBS as a inhibit, like this lesioning of that circuit, or like downregulation of that circuit, or?
Yeah, I think a disruption, or just or a noisy bad signal doing some chaos in the usual activity of this circuit. I don't have this very I don't like talking about it as being a stimulation, right? Though it's in the title of the study is subthalamic stimulation, because it's just easier and everyone knows this wording. But I wouldn't assume that DBS in this context stimulates the STN, but interferes with this circuit. And I think also, again, in the study, it was also a moment where it were three different, I think it was this cognitive domain, the clinical observation, and then of course being close to you and seeing what you were doing with lead DBS and how this became more and more precise and could explain clinical effects. And I think this was also something where I wondered, is this a tool that we can also use to investigate very specific features of behavior and not only broad clinical effects, but also see whether it opens the possibility to investigate very specific effects of DBS. And I wanted to learn more about your methodology. So I think I also wanted to introduce that coming from more a neurophysiology-based approach originally. But I always want to learn how to integrate different methods. So this was
I think you're giving me way too much credit here, and it's really not about me this show. But thanks. But what you did find, I think, if I remember correctly, was that the more people had trouble stopping the movement, the more this stopping triangle was disrupted in a way, right? So exactly was that correctly summarized?
So what I had 2 or 3 readouts, I would say, in this study, right? So Parkinson's disease patients were performing a movement, and we could see how fast they were in performing it. We could measure how fast they were in initiating the movement. So that's 2 very disease-defining features, right? The difficulty initiating a movement and the difficulty in performing movements in high speed. And we could show then that STN-DBS improved this in both cases. So Parkinson's disease patients were faster in initiating the movement, were faster in performing it with STN-DBS, but when trying to stop it, they had more difficulties doing that with STN-DBS than they had without. So they had difficulties, but at least measurable. They were slower in stopping this movement that they were performing when STN-DBS was switched on. And that was the case for all of them. So it's just a large group effect. But then, of course, this effect varies from patient to patient. So some of them are a bit slower in stopping the movement, but others really have significant delays. And this variance then was explained by the location of the electrode. And when the electrode was located close to fibers connecting the STN to the right pre-SMA and the right IFG, then you had more of this difficulties in inhibiting a movement. And I guess that's just the information flow that is then interfered by this external neurostimulation applied to this area.
It's just even now thinking about it just blows my mind how well it replicated the basic science work, right? And you're totally right. I was always like blurring over the other really important findings you also showed in initiating movements and movement speed and so on, and then also in general that on a group effect you have more difficulty stopping the movement. So that is probably as important, but I think that you could even point it to the circuit that was disrupted is pretty cool. Fantastic. So and then I think you had multiple other papers. There was one in eLife, to briefly mention it, where you looked at gamma activity with movement size and movement speed and so on. So and then I think multiple other fantastic papers. But I think the the one that we certainly have to talk about is the most recent one that was published in Nature Communications this year. And if maybe as a backstory, because I still may remember the origins of this study where, and I might remember it incorrectly, but I think the Boston Scientific long electrodes, so the ones, the Versailles, the non-directional ones with 8 contacts that are pretty spanning a large portion of the neural tissue with 8 contacts, when they were introduced, you probably thought immediately or at some point we could record from the striatum if we are in palatal DBS settings, because we have more electrodes that extend up, and that will give us a window into striatal activity in humans. Do I remember that correctly, or?
No, I don't think it was that way. It was
Okay.
So again, it was me reading a paper or papers, and I read the paper by Singh and et al. Back then in PNAS, and they were recording microelectrode recordings from the striatum in dystonia patients. And they showed that there was an increase in or a change in firing rate in Parkinson's disease and in dystonia, and showed that this in the striatum with dystonia patients, the firing rate was lying between in this low frequency range. And given that what we are recording with the DBS electrodes, the oscillations, we think of them reflecting the input to an area. I thought, this makes sense then, that the output activity from the striatum, so the firing rates, are in this range of low frequency activity that we then see in the downstream internal pallidum, where we have decreased low frequency activity. So maybe this is linked. This is a kind of the upstream pathological activity that then leads to this oscillatory synchrony in the internal pallidum.
That makes sense. And sorry for not at all getting that. And just for the listeners to briefly mention, because not everybody might be aware, I think almost everybody will know elevated beta activity in Parkinson's. That is a good marker for bradykinesia, especially, or for hypokinetic symptoms, used for closed loop and so on. Maybe a bit lesser known, but still quite established by now, is this low frequency activity that we can record from in the pallidum in dystonia that seems to also correlate with symptom severity. Not as many studies have shown this. There's one by Julian Neumann that showed it from the same group, and I think probably others too, where just to briefly as a background. So, and you were saying now that you read the paper where they did microelectrode recordings, probably going down to the pallidum in surgery, exactly. Right? Recording on the way down through the striatum, and they found, okay. So and you were making a link between their findings and the hyperactivity in the theta-ish range, alpha theta range.
Exactly. So it's so in dystonia, as you said, in the internal pallidum, which would be the DBS target area in dystonia, or STN can be also a target area, but more frequently you implant DBS than in GPI, and this is why there were studies recording from the GPI and dystonia patients, of course, less than in PD because it's just a rarer disease. But still, it was very well replicated across many studies that in dystonia patients, compared to PD patients, you have an increase of this low frequency activity. And then the studies showing that there is a link with dystonic symptom severity are then there are less studies showing this, but still in the cohort, for example, that Julian Neumann reported on, but also then a work from Stella with chronic recordings showing that there is this correlation between the amount of low frequency activity in the GPI and the dystonic symptom severity. And of course, these were studies from Andrea Kühn's group. And as I was part of the Andrea Kühn's group, I was pretty close to these findings. And then reading Singh's paper was just, I read this and I realized that to go to the GPI, I was back then also assisting the DBS surgeries and performing the intraoperative neurophysiology, realizing, okay, if you want to go to the GPI, you cross apparently the striatum, because they were recording from the striatum. And I think that was not something that I had so clearly made up in my mind, that it was like that. And when I realized that, I thought, okay, but this means then that the DBS electrode that we're planting also lies in the striatum, because that's our trajectory. And I think this was just something that was not so clear to me. And then I just thought, okay, but if we have already this electrode, it would be good then to have, or is there a possibility to record from all these different basal ganglia areas that we are apparently crossing with this DBS electrode, the GPI, the GPE, the striatum, all these multi-sites where we have the DBS electrode in. And this is when I realized that, okay, this device that we already implanted back then, from Boston Scientific, where we have those 8 DBS contacts that are circular contacts, so they're not segmented, so they lie over each other and they span 60 millimeters. And then again, using your tool, Andy, I know you don't want to take credit, but I just localized these electrodes to see if this assumption of mine was true, and then saw, yeah, they're reaching up to the striatum, and then of course it's being a fan of the whole pathway idea of the basal ganglia and the direct and indirect pathway. I just thought, this is so cool. We have multi-site recordings from the basal ganglia in patients, from the direct in the indirect, proxies at least.
Yeah.
The direct and the indirect pathway, and that's.
And the rest was history. No, so super cool insight, and it's even a bit surprising that there are not more studies like this, right? I mean, I guess the Versailles electrode was introduced, and then probably pretty quickly after we had the segmented one. So, many centers switched to that one. So that's why maybe it's not used that often. But I still think I'm personally not aware of a second study that recorded in the striatum using this electrode. So that alone is pretty cool, I think.
Yeah.
And then you maybe also to briefly mention it, I think the striatopallidofugal bundle, so the main axis of the basal ganglia going more or less radially through Wilson's pencils in the striatum, and then these pallidal bundles. It's a massive streamline bundle. I think the electrode would even roughly match that course, right? So you might even think of this as stations.
Correct.
Yeah, well, stations on the same.
Yeah.
Is it? I'm not sure, but probably it would roughly follow these fibers.
I think so. Yeah, at least the axis
cool.
is pretty similar. Yeah. I think that's something that I just really enjoy, I think, in general, when thinking about studies or thinking about projects or research ideas, is to use things that are there and to combine them and to try to make something positive out of restrictions that you have. I think it's that's something that is very different from my clinical work. I think in clinics, I'm just very annoyed by restrictions, or not restrictions in the sense of not ethical restrictions, more restrictions of not having the possibilities to give the care that you want to give, or not having, not being able to help in the way you want to help. And that's something that I think a lot of clinicians are suffering of. But in research, although I can also understand the point of view of scientifics that say, I want to use all crazy stuff and create a lot of crazy stuff, and I want to have these open
Optogenetics, or yeah.
everything. For me, it was something, it's something that I enjoy actually when working with patients, is being restricted in a way, and not being able to put hundreds of electrodes everywhere, and just be
You have
abundant.
to be creative in the choices that you make, or the questions you ask even sometimes.
Because you just have a certain amount of tools, and you just have things that are possible in patients and others aren't, and then you have to be creative on how to still answer the questions that you are asking yourself, and I think that's something that I really enjoy.
See, I've once heard that true artists think like that. So this means you're a true artist. I once heard that if you are a person that builds sculptures from rocks, let's say you want to build a sculpture of a man standing or whatever, right? The real artist would already in the stone see, oh, this could become this sculpture, right? And they wouldn't make it a puppy or something very different, right? So they would use the tool and see the stone, and I think that's a bit what you did there, and leads to the next question. How do you think is the availability of devices, how does that shape what we do in research? Probably it does shape it a lot, right? But new technology, like for example, the Percept device now, enabled, of course, lots of studies. So how do you see that interplay? Are we, is the industry or the available devices, are they restricting us? Are they empowering us? Or how's that interplay for you?
I think as in many cases, it's just a back and forth or an interaction. So, for example, in this study now showing that there is a link between striatal activity and also the striato-pallidal coupling, I would hope that maybe this inspires then new devices, right? So if you're showing that something has a relevance, then of course you hope that the consequence is that more is developed that helps to undermine this relevance or use this relevance. And this was the case, for example, for Percept now, designed to be able to record and to act onto neurophysiological activity from the basal ganglia, which was, of course, inspired by all these studies showing that it has indeed
makes sense.
Meaning. So I think this is always a back and forth, and of course I love it if new things are developed. It's not that I want to just live in the Stone Age and say no, we just have to use what we have. But it's more just my way of thinking that I enjoy to do it that way, and I hope that then other people that enjoy developing new devices can build upon that. But I think people are just different and enjoying different parts of it, and I enjoy puzzling around with stuff that is there and think about how using it and not letting it go to waste.
Love it. And so it does mean we need a strong dialogue back and forth with industry too, which I think is helpful. And it also reminds me of the episode with Nanthia Suthana, who also had to become really creative to, I think, read out some of the signals from the devices and build the backpack, and try to kind of, with the tools we have, to make creative things as you did and Nanthia did. We should summarize the paper, because probably by now the listeners are super curious what you even found. Can you give us the executive summary of that Nature Comms paper?
I think there's one one main result or major result that is based on this idea of pathways within the basal ganglia. So, of course, it's something that's discussed and maybe reductionist, but there's this idea that within the basal ganglia, you have some kind of pathway that promotes movement. That would be the direct pathway that is connecting the striatum with as input of the basal ganglia directly with the output of the basal ganglia, which would be the GPI. And then you would have a parallel pathway that is the idea of balancing things out, inhibits movement, which would be the indirect pathway that has a layover in the GPE and the STN before reaching the output nucleus, the GPI. And in this, in the movement disorders, we have the situation where we have patients that show too much movement, and then we have patients that show not enough movements, right? And those that show too much movements, involuntary movements, dystonia patients that have hyperkinetic movement disorders, and those Parkinson's disease patients that are hypokinetic. And in this pathway concept, there's some kind of emergency, I think, going.
I'm sorry. Let me mute myself. I didn't realize it's that loud.
Close to a hospital. Yeah, so the idea would be then in this pathway hypothesis that you have a balance between those pathways, and in disorders that you have an imbalance. And in Parkinson's disease, you have an imbalance towards the indirect pathway, leading to not enough movement. And in dystonia, you have an imbalance towards the direct pathway, leading to too much movement. And that's an hypothesis that has been based also on neuroimaging results, but there was never really a possibility to have a functional or neurophysiological readout of this hypothesis, primarily also because we don't have, or didn't for a long time, didn't have good animal models of dystonia. And we didn't have the possibility to record from these deep brain structures in dystonia patients, or were restricted to the GPI. So there was not much evidence that was able to support this hypothesis. And what we now did was being able to record from these different basal ganglia structures, having the possibility to weight somehow this indirect pathway to this direct pathway activity by having parallel recordings from the striatum, the GPE, and the GPI. We could show that the striatum and the GPI are strongly coupled in this activity that we already mentioned, in this low frequency activity. And this low frequency activity is present in all basal ganglia, and they're all coupled in this activity, but it is the coupling strength between the striatum and the GPI that correlates with dystonic symptoms. So it seems as if this direct pathway possibly between the striatum and the GPI communicates in this low frequency band, and that if they're kind of stuck in this communication, then there is an imbalance of this direct pathway when compared to the coupling between the striatum, the GPE, and the GPI, which would reflect the indirect pathway. And that's basically it.
It sounds simple, but this was a massive study, and it's super cool. As you say, we've never recorded, we don't have macaque models that are good for dystonia.
No animal models for dystonia, and that's why we couldn't just investigate this. And I think it also puts again the basal ganglia a bit on in the spotlight, because when recording just low frequency activity from the GPI, and you're saying, oh, there's pathologically increased low frequency activity, you don't know where it comes from, right? So it may be something that is upstream from cortex or cerebellum, whatever, that is a pathological signal that enters the basal ganglia. And as we, by whatever reason, have the possibility to record from the GPI, that's where we measure it, but it doesn't mean that it stems from there, right?
Yeah.
And I think the possibility now to record from the input structure of the basal ganglia, the striatum, and showing that in the striatum we don't have this pathologically, or at least we don't see a correlation between the striatal low frequency activity and the dystonic symptoms. So it doesn't seem to be something that just pathologically enters the basal ganglia via the striatum coming from the cortex or the cerebellum, but rather it's this pathological signal is generated within the basal ganglia, in the circuit between the striatum and the GPI. That's where this pathologically exaggerated low frequency activity that is linked to the sonic symptoms is somehow generated.
Super cool.
And that also puts the source of this activity more in this basal ganglia network. And of course, then dystonia is a very complex disorder. And I don't want to say that the sensory cortices or the cerebellum don't play a role in there. But at least for this signature, it seems to be something that is at least amplified within the basic.
Yeah. And the GPE didn't play a role. So you said there is theta activity there too, but the coupling did not correlate.
It does.
With
It does.
symptoms.
The GPE. No,
GPE,
the GPE.
yeah.
It,
So
it,
as the
it's
indirect
there,
indirect pathway.
yeah, I think it's this within the basal ganglia. I guess that the activity spreads more or less everywhere, and and you can detect low frequency activity everywhere. You can detect beta activity everywhere. But the question is in which area it kind of influences or overweights the rest. And low frequency activity, and there's also this the study by the Oxford group showing that DBS in dystonia, for example, doesn't seem to act via the suppression of low frequency activity. So I guess there are different mechanisms of action.
Interesting. And then remind me, did you in that study have some control subjects with Parkinson's as well, or did you offline do that, or any non-public? No, okay, you're shaking your head.
No
insights there. Okay.
No, because we don't have. This would be something that would have been cool, maybe to do with centers in the US or so that implant more in the GPI for PD patients. We don't do that, so we have just a handful of PD patients that receive GPI DBS, and these, I think, in our center all received Medtronic electrodes. However, but this, of course, would be something that I would be very interested in.
So for the listeners, that there's a good study idea here, I think. Although I think even in most centers, unfortunately, this electrode has come out of vogue because everybody wants directional leads these days.
Yeah,
I still think it is a pretty interesting electrode, even therapeutically, not just scientifically, right? I mean, even stimulating in the striatum as a trial could make sense to investigate, and so it has lots of potential.
I'm also I like this electrode, but then it's not the way that was most promoted in the last couple of years.
Although now the HX plus, or one of them is also pretty long, right? Is it a similar span than new electrodes?
So. Yeah.
Okay.
I think you don't have to choose between worlds, right? You can have the segmented and a lot of them and the longitudinal.
Yeah, that's a good point. Okay, so probably also for you more to be done in that direction if this stays interesting. Super cool. Do you think this might, could you speculate if you were an investor now, what would this potentially bring for clinical care? Would there be any hypothetical closed loop application or steering signal, or how would you make use of it clinically, maybe?
So I think the idea, and that's something that in this small group of patients, it was really as usual in dystonia patients, not a very large group, but so we couldn't show it there. But the idea is also that there is a directionality of the signal, right? Because the striatum is thought to be upstream to the GPI. So if we have something that we can record there that is that has a relevance for the symptom generation, it would be, of course, cool to inhibit that or to interfere with that before the symptom is generated, right? So being beforehand and not reacting to a pathological signal, which would be the idea of the closed loop DBS at the moment, is you have a pathological signal, for example, in Parkinson's disease beta, that increases and you react to that.
Yeah.
But this means the pathological activity is already there. Ideally, you would have a possibility to have a readout that precedes that pathological activity. And if we think of low frequency activity that are correlated with symptoms only in the GPI, but not in the striatum, it means that if we have a possibility to decode them beforehand, then it means that in the GPI, they wouldn't be generated, possibly. And this, of course, could be then, I think, a good application for it in clinics. But of course, dystonia is such a complicated disorder, and also the effect of DBS. I mean, it's not something that is that can improve lives tomorrow. Only the device is needed to be designed. But I think it's one way to go, and in dystonia, especially the network activity is just very relevant. So I think that's something where we have to investigate more how the different network nodes are implicated in the generation of symptoms, and also in the and how they which nodes have this effect on the plasticity that is either detrimental or positive for the patients. So we have to remain open, I think, for a network hub recordings in this disorder in order to develop better treatment options.
Yeah, so potentially also with ECOG strips, also to be even more upstream in a way, if that following that same logic. Yeah,
absolutely.
Cool. And so in PD we could in theory think of something similar too, right? It would need to be shown, of course, as well. But maybe there's also some, coupling of the beta signal between striatum and GPI that could be used one day. But that speculation. So
yeah, no, definitely. But then, absolutely. That's also
the market is bigger, so that will make more interesting for the companies, which is in itself, of course, a big topic and also a bit of a sad topic, of course. But dystonia is just a small disorder.
Small disorder, yeah. But I think, for example, this is also one study that I really enjoyed doing was because you talked about beta. Is showing that beta activity also holds its place in dystonia. So we may find something in a very frequent disorder, just as that is Parkinson's disease, for example, but that is also possibly translatable then to rarer disorder, which of course bears a lot of time of investigation if you already have the strong hypothesis, and also maybe helps patients with rarer diseases to profit anyways from results from more frequent ones. So what I'm referring to is just one study where I showed that beta activity in dystonia is linked to slowness of movement in dystonia as well, which can be a side effect of parallel brain stimulation.
Interesting. I wasn't even aware of that. Yeah, fantastic.
Yeah, and just to show that this concept is most likely not something that is then disease specific, but rather can be translated to a lot of conditions where the underlying problem is the same of an imbalance between too much and not enough.
Great. When and where was that published for the listeners that are interested in this?
Last year in movement disorders. That was also a study where I wanted to work with the restricted possibilities that we had back then during the pandemic. So I used video recordings of dystonia patients from our archival data sets and used markerless pose estimation to extract tapping velocity from those videos and correlated it with the intracranial recordings that we had of them, and showed that there was a link between tapping speed and beta activity in dystonia patients.
Super cool. So also computer vision used for quantifying symptoms. Yeah, Pretty great. Okay, so moving on maybe to broader scientific questions. How do you see the field of deep brain stimulation evolving now, particularly, of course, with advances in adaptive and closed loop DBS? What are next big steps, next big developments in thinking broadly?
I think broadly, it would be really to have the possibility to have multimodal data sets of patients, because we now have the possibility of chronic recordings. So we have good spatial and temporal resolution. And I think really combining these different axes of the brain and integrating them is something that I think will allow us really to address this large amount of different symptoms that patients present with in various disorders. I think the disorder then at one point is maybe not irrelevant, but I think there's a lot of translational potential if we have this resolution that we have now, using electrophysiology and neuroimaging in the same.
Super cool. And then what are the next big questions in understanding basal ganglia circuits and their role in motor control? That's related, of course, but more neuroscientific.
Yeah, I think my next, I think now I'm planning to walk out a bit on movement. My next project is would be more related to what do the basal ganglia, what role do they play in sensory processing? Because I think that that's also something that has been not investigated enough. The parallel symptoms that patients present with that have movement disorders in the sensory domain. So they all have a lot of sensory symptoms from multiple domains. And I really want to try to find out how this can be integrated in what we know about movement disorders by using the tools that have been established in the motor domain, and trying to lighten up these sensory symptoms and hopefully also find a way to modulate them, because that's something where I said at the beginning, I like movement disorders because we can help patients with their motor symptoms. But day and day again, I have to see that we cannot help them with a lot of their sensory symptoms, and they're suffering of that a lot. May it be pain or paresthesia or visual hallucinations, or I mean, a lot of things that disable them. And I kind of have the hope that we can maybe use the tools and the treatments that we have for motor symptoms and maybe widen this up to sensory symptoms as well.
So you're jumping across the big central sulcus in the brain in a way. To the other.
No, but it's not a big jump. In the basal ganglia, it's a very small one.
Yes. And visual cortex would be different anyways. Yeah, but yeah, sounds fascinating. My next question would have been what you're currently most excited about in your research. So that is probably that. Or is there anything else? Yeah, okay. What's your favorite scientific book or article?
Oh, that's so difficult to say, but I think also because these are kind of the last questions, right? And we started with the first questions where I mentioned my beginnings in neuroscience and with patch clamp recordings. And I think someone that I never personally met, and I don't want to idealize, I don't want to make a hero cult out of a person that I don't know and of persons in general, but everything and related to fandom that I already mentioned, that I like to be a fan. So I'm a fan of Bujaki.
Okay, yeah.
And his books. And I think I was at the beginning of my 20s, and I remain in the middle.
Which one do you prefer? I think there are mainly two of them, right? Rhythms of the Brain and the Inside Out. So the first one is your favorite?
The first one. But I mean,
Okay.
also because I was young and I loved the world and
Yeah.
I loved this book and I was very happy.
Cool. Fantastic. And so you are right, we're deep into the rapid fire questions already. And one of the questions would have been, if you could collaborate with any scientist, past or present, who would it be?
Wow. Of all of the,
Even past figures. So it could also
no,
say
that's
Einstein.
random. I don't know. I mean, yeah, it would be great to know what exactly was, but I think there would come something great out of it if we could
Yeah.
work together. Yeah, I don't know. Cannot answer this question.
Okay.
So
Yeah. Weird question. I agree. So maybe a better one. Is there a piece of advice you'd share with young scientists interested in neurostimulation research, or if you prefer neurology? And or.
I think it's a very always I always have this very general and not very smart advice that is that you have one life and you should do what makes you happy and what is fun. And I think a lot of times when people in academia start, they feel this pressure and they think about what should I do, how should I behave, and what are the questions that I should ask. And I think at the end, you're really responsible just to live the life that you want to live and work on the things you want to work on. And it doesn't make any sense to do something that you don't enjoy and puts a lot of stress on you for I don't know what bigger reason there is. So that's, as I said, a very simple advice, but I try to say it a lot because I feel that it's not very well heard.
Yeah, I mean, I would say it sounds simple, but it's actually hard to do it, right? I think we do so many of our choices sometimes rely on how we would be seen from the outside, or even how we see ourselves from the outside, rather than really looking out of what are the things in my day I actually enjoy, right? What do I want to, spend time with and so on, but rather we often see, I want to be this person that does X or so, and that's always there's this outside perspective. So I love the advice, and I would still say it's not easy to always follow
And
it.
as I want to be very circular, so we talked about pop culture. So I want to cite here Taylor Swift, who said that you should never be ashamed of your excitement. So if you're excited about something, that's great. Just be excited about it, and don't
Love
let
it.
someone tell you that it's not cool or whatever.
Yeah. It's funny, you are probably one of the people in my life that I know that have the deepest knowledge of as you say, subculture as well, and actual deep arts and so on. But so I kind of love it that you bring up Taylor Swift and Beyonce here, running the risk of potentially being seen a bit superficial, but you're certainly not. And so that's even better. So yeah, and of course, Taylor Swift is fantastic. I agree. So, okay. So, any advice for women in the field? Or thoughts?
Yeah, difficult. For women in the field. So, yeah, I think you just have to be aware that you're a woman and that people just see you as a woman. And even if you yourself don't feel it, it's something where I think you shouldn't be. I think a lot of women tend to say, that's such a basic thing to say, it's because I'm a woman, or they did this because I'm a woman. But unfortunately, oftentimes it's just true. And it's just like that. And I think it just relieves you of some of the burden to try to explain it by your own personality, or no, I did this wrong because I acted that way. And yeah, more often than not, it's not how you reacted or what you did. It's just the way people see you from the outside. But then just befriend the other women and build up your buddy system. And it's very important to have buddies.
Love it. Okay, yeah. Any idea of how one could challenge that or change that, including, of course, how men should behave differently? But yeah.
It's or behave different. I think men should be just respectful people in general,
Yeah.
and women should be too. And then I think everything's fine. And I think it's just important to realize the places you're in. And if you're
Yeah.
in a room full of men, then you should just say something and say it's weird to be in a room full of men, because
Yeah.
usually in this world we have at least 50-50. And I think that's something where just men should be cautious too.
Absolutely. Yeah.
To try to avoid being in those rooms. And if
Yeah.
the room doesn't want to change, then just change the room.
Yeah.
And as a man too.
Yeah. Sounds good. Sounds good. Love it. How does the field of neuromodulation and/or functional neurosurgery of the future look like? What will we do in 10 years?
10 years is not so far away, right?
Can also say 20. You're right. Things are slower than we think, but it's a boring answer to say it will be the same. So let's do 20 years.
So it will be the same. What will be neuroscience? I don't know. For me, it's always difficult to say this just independently. Neuroscience as a module that could move somehow outside of the world where the world should move to. So I think it really depends. We could be at a very great place with neuroscience and have a lot of creative ideas and have things discovered that we cannot even think of, which is very exciting, right? To think that you cannot even project what could be what would happen in 20 years, because there are so many creative minds and so many things that haven't been discovered and they don't even have an idea of that they're existing. But of course, we need the right context to enable that. And I think that's also our responsibility as not feeling isolated as being a scientist, but having the responsibility to create a world where this is actually possible. And this is a respectful world again, respectful to women and men and to nature. And that's something we have all to work to in order to have this very creative fantasy world that I cannot even describe.
Yeah, I mean, there's so many, like, to me, the big two things are AI, where it's very hard to make predictions that go over 5 years. And then also the whole global climate change issue might also disrupt things so dramatically. So you're totally right. It has, like, the basis of life needs to still be there, or like the base of our functioning society. I mean, for things to develop smoothly and positively. And maybe also, again, closing the loop here, I love the idea. Aron, who, came up with the stopping triangle, he at some point, I think, switched entirely to doing climate research, right? So he was a neuroscientist and probably still is to some degree, but switched. That was a bold move, I think.
Something that I'm considering too sometimes. Just think sometimes we should maybe move to very concrete action and put our minds onto work there. But yeah, so certainly maybe I would follow him.
Yeah, certainly the biggest problem we have as humanity, I'm sure, at the moment. And so, you would be the second stopping triangle researcher to shift gears to climate change, which, is certainly a viable option. Okay, any eureka moments you had where you felt like, oh my God, I finally understand X, or this was such a great success, or something like that you want to share?
Eureka moments.
Some have also said it's a moment normally in science where you say, oh, that looks funny, and then things develop.
and then just then. Yeah, I had a lot of those moments. I looked at plots and was like, that looks funny. But then it was just a coding error.
Okay. Yeah, that's the alternative. Yeah.
Yeah, I don't know. I think I can. My biggest eureka moment was just the birth of my child. So I cannot think of anything else because it's so salient in my brain.
Yes.
The moment that all other eureka moments are just.
I love that. That is. I even have a very strong sympathy of that currently. So very much agree. Okay, so but maybe also to maybe even more importantly, to also sometimes speak about failures. Your career has been super successful. You've published fantastic work. Have you also sometimes felt like this was a waste of my time, or this didn't go as well? Just for the listeners to, show that it's not always bright and sunny.
Yes, of course. And I think that's something that actually coexists with the success. It's not something where I could say, this paper or this project went out so great and was published well, so that's just a success story. I think in every story, I always have this very strong coexistence of excitement and failure. And you always have to, and I think it's difficult to navigate that, because failure is just something that comes onto you at night and in the dark moments, and also always wants to shed this dark light on things, and every success can be put under that light. So it doesn't have to be some, even if you think of everything went so well, why do I still question myself, or why do I think I haven't deserved this, or this is not a success? I think it really is in every detail, both sides. And then of course there are just failures in the sense of you didn't get that grant, or you got rejected by, but I don't think that these were really the toughest ones. The toughest ones are more those that are intertwined with your successes.
Yeah, so it's never black and white, and I think you're totally right. Putting a paper out also exposes you to some degree, right? You could be wrong, you could be challenged, you could be even ridiculed potentially, right? And it maybe is I could imagine if you're if you're a composer and the symphony plays it the first time, it probably feels the same way. It's a big success, but then they might also laugh or whatever, right? And there's certainly this. Yeah, that's a good point. Never thought of it that way. So makes sense. And then last question before we stop. Are there any opportunities we should be, like missed opportunities, things we should be doing that we're not as a field? So should we invest more in X or do more of that and we're not doing it?
I mean, I think it's definitely a field that is explored too, but I think we should really work onto using everything that we have. So I think it's very valuable to use, I mean, you're doing it anyway, but I think it's very valuable to look at what data do we have, what do we still have somewhere, and can we use it, and not always build, like, start the new thing, start the new study, I think it's there are so many data and so many stuff that is lying around and is unsexy because it's, I don't know how many years old, but I think data doesn't get old. It's really, as long as your gaze is new on that, I think this recycling aspect of it is something that is not only useful for the environment, but for every situation in your life. So that's something that I appreciate people doing it.
It's music in my ears. I'm even mildly frustrated currently that in almost every grant they make you collect data, right? And sometimes you don't need the data to answer the question because it's already there, and it makes the grant less attractive and less fundable, and that is not a sustainable
and again,
way,
as an
right?
environmental aspect, data, not only because it's not physical, it doesn't mean that it doesn't cost energy, right? To always collect new data, you have to store it somewhere, and that's costful. So I think that's also something that we should consider, is that acquiring data is something that puts also a burden on our environment.
And I mean the cost for an MRI and the running cost, all these things. You're totally right, and then it should potentially even be rewarded by grant agencies if you can do it with less data acquisition. But we won't change that, unfortunately, I think. But it's still good to hear that from you. So before I let you go back to your beautiful family and to Portugal, deserved vacation, is there any topic you would have liked to discuss, or that question that I should have asked but forgot? Or did I cover everything?
No, I think we don't have to speak anymore now, Andy. You covered everything. There's nothing left to discuss.
It was long
between
enough.
us.
Yeah. No, okay. No, makes sense. I took a lot of your time, Roxanne. Thank you so much for taking so much time off and talking with me. And we'll be in touch. So thanks again so much for participating.
Thank you so much to speak with me. So nice. Every conversation I have with you is very nice.
Thank you.